Welcome back. So we are going to now go to the next chapter, chapter 2, which is 3 because I have the introduction here. Chapter 2 of the book. So first, a quick summary of what we have seen so far. This is called the standard inverted index. This is what we built in order to query the documents when somebody looks for specific terms. And remember that the way it works is that we have a set of documents that's basically our library, like the Library of Congress with 100 billion books, maybe. We have the query nicely written in our super Boolean language. And the output is a subset of these documents. So some of them will match the query, some others will not. And for example, this one, and this one are the output of that query. So this is Boolean retrieval. This is the language that I repeat here that is in the EBNF. EBNF, by the way, is just the fancy name to call what this is, right? It's called the EBNF form of the grammar. All right. So, by the way, if you didn't take compiler design, do not worry. This is really for those who understand what this means right there. Otherwise, the only thing you need to understand is that you can basically use not, and, or, and parentheses and terms, and that's it. That's really what that means. Okay. So we abstracted away a few things. This is what I explained to you last week, because we started with documents as lists of words. Of course, if you buy a book and expect to read it, you probably expect to find a list of words in there, right? If you have a set of words or a bag of words, I don't know if you'll go very far or if you'll find the book very interesting, but it's usually a list of words and with duplicates. So what we did is we simplified that to a set of words. What did we do? We threw away the order and we threw away the number of occurrences of the words. So we end up with a set of words. And what we did then is called linearization. We represented the document as a vector of Booleans in our first try. Every document was a vector of Boolean. 1 if the term at that position appears, and 0 if it doesn't. So of course, there's a specific ordering of the terms for the purpose of expressing the vector, right? So maybe this is ETH, this is Zurich, this is computer, this is information, and so on. And for every document, we always have the same order of terms. And then we just mark a 0 or a 1 in there in order to express that. If you're taking the machine learning lecture, that will be totally familiar to you, because this is the sort of things you'll see in machine learning as well when you actually mark your features when you are about to process them. There's just different ways of doing that. All right, so this is just a document seen as a vector of Boolean. Another way to see that simplification is that instead of looking at the document as a list of words, what we did is that we simplified this from an abstract perspective as, I'm throwing the term, a bipartite graph. So what is a bipartite graph? It's just a graph where we have two kinds of nodes, right? So we have the documents right there, we have the terms right there, and we have an edge. If a document contains a term, then we have the edge here. So that document contains that term. This term is contained in this and in that document. So you can also see it as a term document bipartite graph. So these are just logical representations. We also saw that we can represent that as an adjacency matrix. I even gave you a few exercises where you saw that these are the documents here. So here the vectors are like this, vertical, right? And the terms are on the rows. But we saw it's not efficient at all. In fact, there's a lot of zeros. It's extremely sparse. It's extremely inefficient. So we actually abandoned that one and instead went to this approach, the standard inverted index, where we have the terms right there and the list of the documents that contain them, which are the postings, right? So now, how do we see the documents and the terms and the postings in there? Well, the documents here in the bipartite graph, they're on the left. This is a document. In this adjacency matrix, this is a document. It's basically a vertical vector right there with the terms marked as absent or present. And here the document is the postings that have the same number, basically, right? So this is the same document, maybe because it contains all 3 terms. So this is a document. A term is on that side of the bipartite graph. So this is a term. In the adjacency matrix, a term is a horizontal vector. It has the documents that contain or do not contain it, marked as 0s and 1s. And for the postings list, for the standard inverted index, this is a term, right? So the term is one of the entries that we have here on the left associated with the document that contains it. So this is a term. And now the notion of posting, this one is a bit trickier to understand. So pay attention. What is a posting? It's a pair of a document and a term. It's a pair. So this is a posting. It's one document and one term that has an edge there. Right? So it means this document containing that term gives you a posting. It corresponds here to one single one in the adjacency matrix. So we have this one. It means that this document right there contains that term right. This is a posting right there. The zeros here are not postings because the zero is the absence. So when it's absent, there is no posting. The posting is only there when there is an appearance of the term in the document. So these are the ones here, the postings. And in here, this is where it's tricky. This is one posting. It's one entry in the linked lists that we have here. This is a linked list. It's one entry. Why did I say it's tricky? Because if this is what you look at, what you see here is a document. So it could look like, okay, a posting is a document. No. A posting is a document and a term, but the term is right there. It's only because this is optimized, we don't repeat the term every time. So the posting is, we call it a posting, but implicitly it's the pair with that document and that term that is on the left, right? So this is very important, that a posting is not just the document, it's a term and a document that contains that. Right, so far so good. Any questions? So this is just a repetition of what we did last week. So now I have a few questions for you to test your knowledge, and then we'll embark on the new journey. So let me now go to the next. I have 5 questions for you. So, but they look, they co-use the same picture, you will see. So here's my first question to you. This is actually the sort of questions we like to even have at the exam. So it's a good idea if you are able to answer that. This is a standard inverted index, as you can see. And I am asking you the documents that I'm showing below. These are the possibilities. Some of them could have been in the original collection that we have indexed, but some others cannot have been there. Right? So it's like a mystery game, right? So I'm telling you, okay, we had a few documents, we built a standard inverted index, and what we got is what you see on the screen. And now I'm asking you the reverse question: which were the documents in the indexed collection? So you need to look at each one and tell me, okay, maybe it was, or maybe it wasn't in the original collection. So here we have a document A that contains the term 128365. Here we have a document 2 that contains the terms A, C, F, and E. We have a document E that contains the terms 274732374. So in that case, I'm basically giving you the book, right? What there is in the book. Book number 3, document 3 is ABD, document 2 is ACCEAF, and document 4 is BCEFGEF. So some of these documents were in the original collection of my books, and some others cannot possibly have been because that would be inconsistent with the index that you see here. All right, so go ahead, tell me. I'm giving you a bit of time for that. We already have a few answers. So for some of them, it's going to be easy, right? Because maybe some of the answers don't make any sense. So these are the ones you can immediately eliminate, right? But for some that make sense, then you need to look closer at the standard inverted index. These are the documents, just projecting the index so that you see it in big. let me show your answers if you want to start comparing what you have entered. So there is a bit of a consensus on two of the documents that a lot of you like. And for some other documents, very few. So you still have a chance to change your mind. Right, giving you a few more seconds, then I'll show you the solutions. Okay, let's stop. So the majority is correct. So first of all, congratulations. So you found out. So my first question to you, some of them didn't make any sense. Which ones did not make any sense at all? And that you could directly get rid of? Anybody? Documents A and E, exactly. Why don't they make sense? Exactly, A and E are terms. How do I know that? Because it's a standard inverted index. So you see the terms are on the left here. These are the yellow rectangles. So in that case, I'm using ABC for the terms and I'm using numbers for the document IDs, right? Of course, it's a matter of convention. Maybe I could have used numbers for the terms and letters for document IDs. But I mean, since you know how a standard inverted index looks like, then you know that what is on the left is the terms. All right, so we can already eliminate two of the answers. Now, let's take one that actually works. Document 2 has A, C, F, and E. How do I see that it's compatible with this? Well, look at A here has the number 2. C has it as well. You see C has the posting right there too. So the posting C2 would be the posting. E has 2 as well here, and F has 2 as well. But it's not enough. You also need to check that the other terms do not contain 2. So you also need to check that B here does not have 2. So you can see since it's sorted, it's quite easy to see here. So you see that 2 is not there. D also doesn't have 2. E and F are in A. G also doesn't have 2. So you see, this is how you know. So document 2, ACFE. The other one, document 2. In that case, it's actually the same document. So here you're basically saving you the thought. It's the same set of words. It's not the same book. Basically, it has the same words, but in a different order and repeated differently. But if you look at it from a set of words perspective, it's also A, C, E, and F, right? So if the first document could have been in there, then the second one as well, right? Which one of the two was actually in the collection? Can you tell me that? This one or this one? Which one was in the collection? Anybody? Can anybody tell? I'm going to tell you, nobody knows. The answer is that nobody knows. And why is that? Is that when we build the standard inverted index, we lost the information about the order and the occurrence of the term. So we basically cannot tell anything just looking at the index. So this is the reason. It could be the one, it could be the other, maybe yet another one. So this is why I was careful in the question, right? I said could have belonged, and I didn't say did belong, because we cannot be sure. All right. Now, document 3, ABD. Can anybody tell me why document 3 cannot have been there, A, B, and D? Because here I see the 3 for A, the 3 for B, and the 3 for D, right? So how can it be that the answer is no? Dan, do we have in the Zoom chat?
Because it also contains E.
Yeah, absolutely. You see the 3 in there? It means that document 3 that was indexed also contains the term E. And you can see that the document proposed here doesn't have E. So this is why we can say that it's not in there. And for document 4, how do we know? BCEG F, basically in there. How do we know for document 4?
From the chat, G doesn't have a posting for 4.
Yeah, that's exactly it. So you see G here doesn't appear in document 4. So that cannot be document 4 because it has a G in there. All right. Okay. So that should make you already familiar with the thing. So let me now ask you an easier one. So it's going to be shorter. If I ask you A and B, what documents does it return? That should be fast. That should be a very quick answer. A and B. Documents that contain the terms A and B. Right. This is supposed to be an easy one, right? So of course you need to mentally use the intersection algorithm. And almost all of you got it. You still have a chance to change your mind if you answer 3-9. And indeed, the correct answer is 3-8. How do I know? I took the posting list A and B here, and I just used the intersection algorithm that I told you about. So then you see that 3 and 8 are the only ones that are in both. 9 is not, right? So 3 and 8 are the two results. Okay, another easy one, C or D. What does that return? That should also be a quick one, very quick one. C or D. This time it's the union algorithm, right? Let's look at the live results. Wow, 100%, same answer. That's really, really great. Everybody's following. So indeed, it's the correct answer, right? It's the union of these two here. 1, 2, 3, 4, 5, 7, 8, 9. Okay, here's another one. D and not E. Can you do that one? A bit more time for that one. D and not E. So the documents that contain the word D, but not the word E. So it's basically the intersection, but for E, you need to mentally invert it. So you need to basically negate what is in there isn't and what is not in there is. All right, and here we have 100% as well, so I might as well tell you the solution. Indeed, it's 1, 5, 8, 9. The 3 is disappearing basically from here, and you see that because that's the only one that is in, right? So 1, 3, 8, 9. And to finish, for that round of questions, this is one where you need to basically think a little bit more. This is the query A or B, and E, and F or not G. So remember the technique that I showed you to optimize, how to quickly see what you're supposed to start with. Of course, you're not a computer, right? So maybe you're not going to compute it exactly in the way the computer will, but still that should guide you in order to accelerate. So what is your starting posting list? Anybody? Which posting list did you take as a start?
So in the chat, there is an answer, F
Yep.
or not G.
F or not G. So this is what you started. Anybody else? Any other strategies? So F or not G, we basically would start with that, right? F or not G. Any other ideas?
Another answer is E, also from the chat. And then another
Yep.
one is E, then A and B, then F, not G.
Yeah, all right. Yeah, go ahead.
Another one is A or B, is just 1, 9.
Okay, so let's discuss that. That's a great start. So first, E is indeed the start. Why E? Can you tell us why you picked E first? It's the smallest, exactly. So this is indeed where you can start 2, 3, 4, 7, and then you can quickly see that they are both in A and B. 2, 3, 4, 7, they are all in there. And then you can see that 2 and 4 are in F, so they qualify for the third one, and 3 and 7 get kicked out because they are in G. So this is how you end up with 2 and 4. Now we have a few interesting comments in there. Somebody tells us A or B is just 1 to 9. So all the numbers from 1 to 9. So indeed, as a human, of course, for a computer, it might take longer to realize, but if you look at a human in there to A or B, indeed, you realize that it has basically everything. So what that means is that you can throw away the A or B because you know that everything is in there. So you don't even need to bother with the intersection. Yeah, so I think that's perfect. And F or not G, you need to do the merge, but you need to realize that the size of that has at least 6 with F, and it has 5 more potentially. So 6 plus 9, 6 plus 5 gives you at most 11. Well, of course, 11 is above 9, so that cannot be 11, but that's the worst upper bound, basically. You have an upper bound of 9, which is all of them. So this is the reason why maybe F or not G could be maybe the second one, but not the first one. All right, but I hope it's clear to everybody. And we got a very good majority here with 2 and 4. And for those who answered 2, 3, 4, 7, I hope you understand why that's not correct, right? It's because 3 and 7 are actually in G, and there is a knot here. That's the reason. All right. Okay, that's enough questions for now. I hope it helps you consolidate what we've been doing. So we are back. All right. So last time we had this idea that we have these documents, we simplified stuff and did some magic trick like Harry Potter stuff, and then ended up with this standard inverted index. But this is not reality. We actually oversimplified everything, and it's more complicated than that. Actually, now I'm going to show you why it's actually more complicated than that. Because in reality, we start by collecting the documents. That alone is a challenge. I explained to you in the antiquity how complicated it was to actually gather the documents. So you need to purchase them as a library and so on, or download them on the internet. That is already a challenge, downloading the data from the internet and finding it. Then you need to tokenize, right? It's when you cut, we did it with spaces last time, right? But I will show you today, it's not that simple. You cannot just rely on spaces, right? It was a simplifying assumption we made. We have the linguistic preprocessing, which is that because of the different languages that we have, they have different way in which they work, and we will see it's actually not easy at all, right? So I assume there's plenty of different mother tongues in the classroom, probably plenty of German, Swiss German, English, French, maybe Italian, and all over the world, but we'll discuss a little bit languages. And finally, we built the index with the posting list. And this is actually more complex than it seems. Of course, in a small scale, that's what you will do this week. But if you have 100 million books, then you will see it's more complicated. But this is something I'll come back later in a few weeks, the complexity of building these large indices. But let's come back now to the start, the documents, collecting the documents. As I said, that already is complicated. So first, because you need to search for the documents you want to index, you need to download them. Downloading in itself, you need a good bandwidth. Maybe the volume is going to be enormous. You need to find some storage if you have a lot of that. But even when you do, a first challenge is that you need to parse these documents and read them. And that already means you need to open them. And the first challenge you get is how do you come up with these characters in there? Because it's always stored as zeros and ones. So of course, if you just open it with a text editor, if it's a simple English one, then maybe that's just going to work, right? It opens it character by character with an encoding. But in fact, it's not trivial because, as you know, you're computer scientists, right? You know all of that every character that there is right there is actually encoded as a sequence of zeros and ones on the disk. And in that case, we use the ASCII encoding where we have 8 bits for every one of the characters. And this is how the document was actually parsed, right? So this is not the way it's stored. This is already a logical level that the text editor shows you, but on the disk, it was like that. So I have a question for you just to test your knowledge, because I know you're computer scientists, but I just want to check one thing with you about your knowledge of encodings. So now if I come back here and ask you this, I'm giving you 4 answers: Unicode, ASCII, UTF-8, and macOS Roman. One of these is not an encoding. Which one? What do we have? Oh, macOS Roman. So 80% says macOS Roman, but 20% said Unicode. You have a chance to change your mind. Now, there's a bit more in Unicode. Be careful, the majority is not always correct. Now the minority is increasing. We have 26%, 30%. All right, doesn't change anymore, so I'm going to stop. Yes, this is the correct answer, Unicode. Why is that not an encoding? What is Unicode?
From the chat, it is a standard.
It is a standard, indeed. What is in that standard? All right, so I'm going to explain. So basically, what there is in there, oh, there you go. I thought I lost my set of slides. I wanted to come back. So Unicode is actually just an enormous catalog. It's really just a list of characters that have a number. This is character number 1, this is character number 2, this is character number 3, but actually a gigantic list. Actually, it's character number 1,200,000, blah, 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 blah. So it's a huge catalog of characters, but it's really just a list by numbers, right? So of course, it starts with ASCII characters and so on. Then you have the A-umlaut, O-umlaut, then the accent aigu and so on in many, but then you have also Chinese characters, Devanagari script, Arabic, and so on and so on. Right? So you have plenty of that. So there's an enormous amount of characters. And recently, I think the working group probably spends a lot of time on actually adding emojis to this list, because they also get numbers, the emojis. That's the reason why you are able to actually use them when you speak to each other, when you write to each other. But what's important is that this is all it is. It tells you absolutely nothing about how this is mapped to zeros and ones on your hard drive. And the reason is it's UTF-8, UTF-16, UTF-32. These are the ones that actually do the encoding of Unicode. But Unicode is really just a catalog. That's all it is. So this is the reason. All right. There you go. All right, so you have your ASCII table. These are the simple ones. And Unicode actually also starts with that, right? So this is something I'm assuming you know. Again, that's pretty standard in computer science. This is when computers started. These are the ones we had. And then you can convert anyone to a hexadecimal notation to zeros and ones. But UTF-8 is actually more interesting to look at, because what happens with UTF-8 is that it's elastic. It basically extends depending on the character you have. So this is why I'm saying this is not the same as Unicode. Because if you have at most 7 bits, I should have said at most and not less here, because it can also be 7, at most 7 bits, then what you do is that you put the 7 bits in there and you put a 0 in front. So in that case, it's 8 bits. It turns out to be the same as ASCII actually. And that's the reason why when you open in an editor, you might see these strange characters from time to time, because you might not be opening it with the right encoding, but still some of the letters still show. And this is because it coincides with ASCII. That's the reason why you still see these letters. Then if you go and have at most 11 bits, look at what happens here. We cut it into 2 parts. We put 5 of the bits in there and we put 6 in there. We pad with zeros if necessary. And what is the idea here is that we have these bits here that tell us 110. That means be careful, there's 2 packets. That's what it says, 11, 2 packets. And the 10 here is the continuation flag. It tells us this is another packet, but it's not standalone. It belongs to a series of packets, right? And then you generalize. If it's up to 16 bits, then you have 1110 here. That tells you, okay, there are 3 packets, 1, 2, 3. And then you have this 10 again, that's the continuation flag in there. That tells you this is continuation. All right, so this is UTF-8. You also have UTF-16, UTF-32, so there's alternatives. But by default, whenever you create documents or start a program and so on, you should really start with UTF-8 or that sort of international encoding. That will save you time when you need to do it later, when you switch to an international coverage. All right. Okay, so, but why is it challenging? Well, first, it's challenging because it's complex, but the problem is that, as you might understand now, maybe the documents will not mention its encoding and you don't know, it's just zeros and ones in there. Maybe you're an archaeologist and you don't even have the complete document, right? So you need to do what you can. And you need to figure out, is it ASCII, is it UTF-8, is it ISO Latin 1, which was one of the first to add the accents? We don't know. Which makes me realize now it's the break. So I'm actually supposed to stop talking. Let's go for the break, 15 minutes. I'll continue talking at 3:16 after the break, and we'll take it from there, right? So see you in a quarter of an hour.